using trig functions to model and solve problems. So our first problem here is the easiest type of question because the equation is given to us. And whenever that equation is given to us, well, then we can just use DABC to graph it completely. So we've got our equation. Our depth is negative 4.5 cos 0.16 pi t plus 13.7. Sketch the graph. So just for reference, I'm going to write DABC here. How do we use DABC to sketch our graph? Actually, I'm going to move this line down a little bit, because I can already see where my center line is. My center line is going to be at 13.7. So I'm going to choose an arbitrary point here. I'm going to say that happens to be perfectly 13.7. That's my center line. So I draw a red dotted line at 13.7 to represent my center line. That's all you have to do for the D part of DABC. The A part of DABC says use your center line and your amplitude to mark your maximum and your minimum values. So if my center line is 13.7 and my amplitude is 4.5, so when we talk about amplitude, amplitude is always a positive number. Even though there's a negative 4.5 in front, we would say that our amplitude is 4.5. I use my center line and my amplitude to mark my maximum. So 13.7 plus 4.5 be 18.2 minus 4.5 will be 9.2. That's all you have to do for the A. Your B value helps you find your period. Your period is 2 pi divided by your B value, which in this case has some very not nice numbers. 2 pi divided by 0.16 pi. Those numbers are not nice enough that you'd be able to use your calculator for this. I believe you get 12.5. So what we're going to do is we're going to mark 12.5 somewhere along our x-axis and divide it into 4 equal sections. So half of 12.5 is 6.25. Half of 6.25, 3.125. And then this one will be 3.125, 6.25. This will be 9.375. So with your B value, you find your period. You mark your period and separate it into 4 equal sections. The next part is the dash. Even though you don't say it when you say DABC, you have to do something with the dash. That means you temporarily draw it without any translation. So this one is a negative cos graph. Where does a negative cos graph start? A negative cos graph starts at a minimum. And then you just alternate in each of your sections. So if I'm at a minimum, at the next section I'll be at my center line. Then I'll be at my maximum. Back to my center line, and then back to my minimum. So this is my cosine graph before I have any translation. So that's the dash part. And finally, you do any kind of translation that's needed. But in this one, do you see that there is no translation? So our dotted graph is actually our final graph. The next thing I would like you to do is to take this equation and type it into your graphing calculator. because we're going to solve part B. A bulk carrier needs at least 14.5 meters of water to dock safely. So if we look at our graph, and if this is the depth over here, I should have labeled these things. This is depth here, and this is time. And we should put in our units. This is in hours. Depth is not in kilometers. No. In meters. If it needs a depth of 14.5, 14.5 would be about here, 14.5. And I'll draw the water level at 14.5 like this. Can you see it's only in this section here that the water's deep enough? So we're going to want to figure out for how long per cycle can it dock safely? How long is it from here to here? And we're going to use our graphing calculator to solve for that. So the first thing I need you to be able to do is I want to see this graph exactly as it is here on your graphing calculator. So when typing things into your graphing calculator, one, you have to make sure that your mode is in radians. For all of our sine and cosine graphs, our mode will be in radians. Okay, is this working? Yes. So I'm going to check, is my mode in radians here? Or it doesn't let me change? Mine is crashed. Oh, it is in radians. Guess we'll just ignore that then. So y equals, and we'll type everything in, negative 4.5 cos 0.16 pi. There is no t, but you use x instead, plus 13.7. Now, if you go about graphing this and push enter at this time, you might get exactly the same thing that I have. Or a, you see the graph? Oh, there it is. Does that look the same as this graph? No. What's the problem here? The problem here is that the window that I'm looking at on my graph is this window. That's why I only see that little part. I want to see the graph exactly as I see it here. How do I do that? How do I change it so I don't just see the little, see that little blip? That's all I see, the little blip. How do I change my graph to see everything that I want to see? Well, on your graph you have a window. So you do need to be able to graph this by hand first before you can go to your graphing calculator, because otherwise you might be searching for a very long time to be able to have it show up on your screen. What we've done here by graphing it is we've realized what kind of window we want. So when I go to my graphing calculator and I go to window, I can say I'm really interested at looking at from 0 to 12.5. So I'm going to maybe do a little bit smaller than that so I can for sure see my y-axis. So I'm going to start at -3 and I'll go up to 15. So a little bit more on either side, because that will show me between 0 and 12.5. You may never have used this X scale thing before. All the X scale thing is telling you is where it puts its marks. So when it's set at 1, it'll put marks at 1, 2, 3, 4, 5, 6, 7, 8, 9. If I want these marks exactly as I've written them here, I'd have to set my scale to 3.125, because that's what one of my marks is. So I'm going to do that just so it really matches up with my graph. For my Y scale, I don't need to see down to -10, so maybe I'll just do a couple in the negatives so I can for sure see my x-axis. My maximum was at 18.2, so I'll need to go up to a little bit more than that to make sure that I see my maximum. For my Y scale, I can keep it at 1 if I want, let's push graph and say, does this look similar to the graph that we graphed in black? Things match up quite nicely. So I'm going to show you that you can use your graphing calculator to find this out. Now, based on our graph, we would need to know at what time it's at this point on here, and at what time it's on this point there. And if we could find those two times, we could subtract them, and then we could solve for how long the bulk carrier could be safely there. The water would be deep enough during those times. On your graphing calculator, you have the ability to graph more than one thing. If I want to draw a horizontal line, horizontal lines are always y equals, I can type in 14.5 into y2, and that will draw a horizontal line at a depth of 14.5. And now I want to find out where those two graphs intersect. And again, your calculator has built into it a lot of strategies and things and solving capabilities. For graphs, they're all under Calculate, which is above the Trace button. So hit your second button and then your Trace button. And number 5 is Intersect. Either push 5 or hit Intersect. And once you get on your curves, it says, which one do you want to be your first curve? So push Enter. Which one do you want to be your second curve? And it goes to the second one. Push Enter. Guess. It always asks you to guess. I think they're going to intersect here. And then it finds whatever intersection is the closest. Okay? Take your computer's calculator screen, just drag it to your notes, just like that. And we've got our one value. It says it happens at 3.48. That's our one time. If we do this and find our second one, so I'm going to go back to my calculator, and I'm going to calculate the second one. So I go second, trace, and I want to go 5, intersect. If I push Enter on first curve, second curve, and third curve, it's going to find the same one. Like I said, it always finds the closest one. So you're going to need to move your cursor. I'm doing mine slowly because it sometimes crashes. Okay. I think now it's closer to the other one. I push Enter, Enter, guess again, and yes, it did find my other one. And according to this one, it's at 9.02. So the one time is at 9.02, the other time is at 3.48. I can write a statement for a word problem. It can dock safely for 9.02 minus 3.48, which is equal to 5 hours at 5 point. It can dock safely for 5.54 hours. So the graphing calculator is powerful because it can get us answers like this right away. Now I'm not going to get you to write this down, but I'm going to show it to you because often when you get to university with a question like this, they're going to expect you to solve it algebraically with only a scientific calculator and not a graphing calculator. So you won't have this ability just to graph both, find the intersection, and say what it is. But you do have the skills already to figure this out. I'm going to show you what it looks like. Again, it'll be on the video. Don't write it down. You start by setting up your equation. You know the depth is 14.5, And if you want to find out where those things intersect, you could substitute 14.5 in for your depth into your equation. And what you want to solve for is t. So you're going to use your algebra skills with sine and cosine and solving trig equations to solve for t. Well, what does that look like? Well, if I'm solving a cos equation, I would want to get cos by itself. So I'll move the 13.7 over to the other side, divide both sides by the negative 4.5. That gets me the cos by itself. Now, the one thing we haven't done a lot in our algebra up till now is solving questions that look like this, with a bunch of stuff inside of cos. That gets a little bit confusing. What we've solved up till now have always been like cos theta equals, and that's a lot easier. So we actually do the same thing here. To make it easier, we just say, well, it would sure be easier if it was cos theta equals, so I'm just going to let theta equal all that crap on the inside. Because then my equation looks nice and simple, and I've done that before. If I have cos of theta equals 0.8 over negative 4.5, I've done that before. I've done it in radians, I've done it in degrees. First thing, is that on your pie plate? No. So it's a calculator question. You would have to find your reference angle. How do you find a reference angle? Cos inverse of the positive values. If you wanted to draw the triangles, cos is negative in quadrants 2 and quadrants 3. So once you get your reference angle, you would have to find the angles in quadrant 2 and the angles in quadrant 3. Quadrant 2, it would be pi minus your reference angle. In quadrant 3, it would be pi plus your reference angle. So that's solving for theta. That you've done before. What's the difference in this question is we made theta equal to all of that crap on the inside. So now if I wanted to find out what t is, if one of theta is equal to 1.7495, can you see that 0.16 pi t would equal 1.7495? And if the other theta is equal to 4.53313 less 7, then 0.16 pi would equal 4.5337. So doing that next, doing quadrant 2 first, well, how would I solve for t? I'd have to divide by 0.16 pi. So divide both sides by 0.16 pi, and sure enough, we get our 3.48 t, the same as we got from our graphing calculator. Do the same thing with the quadrant 3 angle. Divide, and you get your 9.02. So we could do this algebraically and get the 5.54 hours the same way that we did with our graphing calculator. This just takes a lot longer. But it's important to see this because once you get to university, they're going to say, no to the graphing calculator, we want to see your algebra skills. Then you're going to be expected to solve things like this. All right, let's go to example 2. Example 2, you've got a Ferris wheel, a radius of 15 meters. So here's our Ferris wheel. It's rotating every 20 seconds. So just like the example that we saw at the beginning of class, we're going to have to draw a picture of this, draw a graph, and then find its equation. So let's start with our picture. Here's our Ferris wheel. Better add spokes, otherwise nice comfy chairs. Excellent. And right beside my Ferris wheel, I'm going to draw my graph. So I've got my ground level right here. I can put my height here, time down there. This Ferris wheel has a radius of 15 meters. So if I label that on there, I know that that's 15 meters. Passengers start 1 meter above the ground, and it rotates every 20 seconds. So some things that I know on my graph already. I know that 1 meter above the ground is where I get on it at the beginning. If it takes 20 seconds to go all the way around, if I mark 20 here, I know that 20 seconds later, I'm going to be back all the way around. How high am I going to be at 10 seconds? Right here. 10 seconds is half the time. I'm going to be right at the top of the Ferris wheel. How high is that going to be? 31. Because our radius is 15, so our diameter will be 30. We're already 1 above the ground, so at 30 above 1 will get you to 31. That tells us that our center line in this one is at y equals 16. I mean, again, you can use your amplitude. That means your radius. You could go up 15 to find your centers at 16. And at 10 seconds, you're going to be at the top of this Ferris wheel. Now, 20 seconds represents the period, so one of the things that we've always done when we've graphed sinusoidal graphs is we've divided our period into 4 sections. So we've already cut it in half. Cutting it in half again will give us 5 and 15, and that's when you would be halfway up. So we've taken our situation, we've taken the information given to us, and we're able to draw this graph. Writing an equation for this graph requires us to think about DAB-C. What's our center line? Well, we already drew that in. That's already 16. What's our amplitude? We already talked about that being 15. So your D and your A value are really easy to figure out. Your B value is always 2 pi over your period. And my period in this situation was 20 seconds, and so my B value is going to be 2 pi over 20. You could reduce that to pi over 10, but I actually prefer 2 pi over 20 because when I see 2 pi over 20, I can see the period be 20 right in that fraction. So it tells me more than a pi over 10 is a simplified one, but it doesn't tell me as much. Because your period is always 2 pi over your B value, and your B value is always 2 pi over your period. So when I write it as 2 pi over 20, I can see that my period is 20 right away. Now, when writing an equation for this, you have lots of options. We're going to write 4 different equations for this. We can write sine and cosine, and we're going to write a negative sine graph and a negative cosine graph. The only thing that differs between different types of sine graphs, cosine graphs, negative sine graphs, and negative cosine graphs is where the point starts. A sine graph, if we start with our sine graph, well, I'm going to start with all of them actually, just to show you something important. For my sine graph, my A value will be 15. My B value will be 2 pi over 20. I haven't written in my C value yet, but my D value will be 16. For my cos graph, my A value will be 15. My B value will be 2 pi over 20. Haven't written in my C value yet. My D value will be 16. For my negative sine graph, my A value will still be 15. My B value will still be 2 pi over 20. and my d value will be 16. And for my negative, oh, I said negative sine and I wrote cos. And for my negative cos graph, my a value will be 15, my b value will be 2 pi over 20. I haven't written in my c value yet, but my d value will be plus 16. The reason I wanted to show you all four of these at once is because when you work backwards from DAB C, your amplitude, your center line, and your period which gives you your b value are the same, whether that's a cosine graph, a sine graph, a negative cosine graph, a negative sine graph. The only thing different when you choose to write a sine graph is a starting point. And a sine graph starts on your center line going up. So now I look at my graph and say, there's my point where my sine graph, it's on the center line going up. That's shifted 5 to the right. So when I write my sine equation, I'm going to need to show that translation of 5 to the right by writing x minus 5. If I'm looking for my cos graph, so I'm going to write a little 1 here to represent that that was equation 1 that matched up with. My cos graph starts at a maximum. Well, there's my maximum. So if I want to write a cosine graph, I need to shift 10 to the right. So I'd have minus 10 in there. A negative sine graph starts on the center line going down. So if I'm looking at my graph now, do I have a point on my center line going down? Yes, right here. I'm going to call that equation number 3. And that's shifted 15 to the right. And finally, if I want to do a negative cos graph, well, a cos graph starts at a maximum. A negative cos graph will start at a minimum. Well, and we're already starting at the minimum, so I could just leave this, or I could write plus 0, but I wouldn't need to write that. That would be another equation. When you're asked to write any equation, sine or cos, you can choose whichever one you want. Some people like the cos graphs better because it's easier to find maximum and minimums than the center line. Some people like sine graphs better because they're like, well, they're called sinusoidals, so that sounds like I should use sine more than cos because they're not called cosinussoidals. Yeah. But you can choose. Okay, I want you to try the Ferris wheel question. Well, let's finish this one up. It's graphing it. They have some estimating questions we haven't done. Let's finish this up. Estimate the height after 22 seconds. An estimate says just look at your graph. 22 seconds is right here. If we looked at our graph and estimated it at 22 seconds, well, it's going to have gone back up. Maybe I think it's at 5 meters. That would be a fair estimate based on your graph. If we wanted to find this exactly using our calculator, now that we've got all of these equations, we can take one of these equations and type it into our calculator. So I'm going to clear things out here, and I'm going to type in this last one, negative 15 cos alpha fraction, make it look exactly like I have it in my notes, 2 pi over 20 x, close that bracket because I don't have to do plus 0, and then have plus 16 afterwards. Then I'm going to think about the diagram that we drew, and I'm going to go to my window, and I want to see, maybe I'll go from negative 5. I want to see past 20. I'll go up to 25. I'll make my scales go by 5. For my y values, it goes up to 31, so I'll make it go up to 35. Hit graph, and there's our Ferris wheel ride, just like we've graphed it. So at 22 seconds, we looked on our graph and estimated 5 meters. How do you find that exact value with your calculator? Again, you can go second, calculate, and the quickest one there, number 1, just put in any x value. So if I type in 22, it tells us it was 3.86. So our guess at 5 was pretty close. So we estimated it, and then we actually calculated it. Same thing here. Estimate at what time you will be 20 meters above the ground. So if we go on our graph here and look, where's 20 meters? About here. You're going to be 20 meters above the ground there and there. So I'm going to say at about 6 seconds. Now, since this is symmetrical, if I say it's 6 seconds, can you tell me exactly what this one should be? 14. Because it's symmetrical, if this is 1 away from 5, this one have to be 1 away from 15. How do we find this exactly on our graphing calculator? Well, we can go to y equals. We can't do a value this time, but we can put the line y equals 20 into our graph, which draws that horizontal line at 20. And now we can find out where they intersect. Second, calculate number 5. Enter, enter, enter. 14.14. So if it's 14.14 on that side, which is 0.86 away from 15, the other one would be at 5.86. You could also find the other one by doing second, calculate, trace again, and just moving your cursor closer to that other one, 5.86. So our calculator is very powerful for helping us find out what these things are exactly. Our drawing gives us a sense so that we can estimate it. And again, we need to be able to draw it first in order to even put it into our calculator in a form that we can use it. So like I said, I'd like you to turn to example 2 on the ones try on your own, the Ferris wheel one there.